Always when you come in, there should be a question waiting for you on the Socrative app, and that's a way for you to check your knowledge. This particular one reads, which of the following descriptions reflects the proper preparation of 500 milliliters of 0.500 molar sodium hydroxide? And to kind of help you out and save a little time, you were given the molar mass of NaOH as being 40.00 grams per mole. So if anybody wants to check their answers, get yours locked in here, please. Count down, 5, 4, 3, 2, 1. Correct answer is choice D. We're going to dissolve 10.0 grams of sodium hydroxide in enough water to make 500 milliliters of solution. What's wrong with C?
You have too much.
Too much what?
You'll have more than 500 milliliters.
Right, you're going to have too much solution because at the end you want a total of 500 milliliters of solution. Remember, this is the Kool-Aid rule. Look at a package of Kool-Aid. It says it makes 2 quarts. It doesn't say it makes 2 quarts plus whatever Kool-Aid you dump in. It makes 2 quarts. But if you go through, then you should be able to verify those calculations. Okay, now in your packet, I don't think we'll get through the entire packet here today. In fact, as you look at the packet, I think the last class we did everything except the bottom of page 2. Page 3 is one that you will be going through on your own. So page 3 on your own, I don't think we'll have time to get to that one. And then the back side, we'll be doing some of that stuff here today. So let's look at this particular one. This is from page 188. This is question 3.65. It says to consider the precipitation reaction showing 2 moles of sodium phosphate reacting with 3 moles of copper 2 chloride reacting to produce copper 2 phosphate and 6 moles of sodium chloride. And the question is, what volume of 0.175 molar sodium phosphate solution is necessary to completely react with 95.4 milliliters of 0.102 molar copper 2 chloride? So as I read through this thing, the things I would probably identify, first of all, is what is it we're looking for? So that's the first piece. What are we looking for in this one? Volume. And the volume of which stuff?
Sodium phosphate.
Right. We're trying to find the volume of this stuff right here. And if we're trying to find the volume of that, I guess we might look through and read the problem and see if there's anything else we can discover. We do see a couple quantities separated by the word of. And what does that of tell you we'll probably be doing? Multiplying, exactly. So again, whenever you see 2 quantities separated by the word of, that means at some point we'll probably be multiplying those together. And that would actually probably be the best place to start. So we'll start with a 95.4 milliliters of the 0.102 molar copper 2 chloride. And at some point here in our answer, we're trying to get to the milliliters of the sodium phosphate solution. So that's where we're trying to work towards in this problem. Now, of course, when we have these 2 quantities here and we want to try to multiply them together, it doesn't look like we could do a whole lot with the units. So we need to remember what big M stands for, and that is moles per liter. So I would go ahead and substitute right away big M for the molarity with moles per liter. And of course, remember, this is the milliliters of the copper 2 chloride solution, and this is the moles of copper 2 chloride per liter of the copper 2 chloride solution. Well, now we're getting a little closer to getting units to cancel. This here is liters, this here is milliliters. Now you can do it one of two ways. You could either convert this to liters, or my preference is to convert this down here to units of milliliters, because 1 liter is the same as 1,000 milliliters. And of course that's the same thing you'd wind up doing if you would have converted this to liters, because you had 95.4 milliliters. To get the number of liters, you would have had to divide it by 1,000 anyhow. So it's the same effect. It doesn't matter which of the two ways you wind up doing it. To me, this is always the easier way. So now we have moles of copper 2 chloride. We're not trying to find the copper 2 chloride, however. We're trying to get this over to the sodium phosphate. So how do we get from copper 2 chloride over to the sodium phosphate? What is that conversion called? Molar ratio. So we want to go back here and find the molar ratio that relates the copper 2 chloride to the sodium phosphate. To do that, up above we're going to put which stuff?
Sodium phosphate.
Sodium phosphate. And how many, or how much?
2 moles.
2 moles. And on the bottom we put 3 moles of copper 2 chloride. Good. And again, those come from the coefficients here in the balanced chemical equation. 3 moles to 2 moles. The units here wind up canceling out. Now at this point we have moles of sodium phosphate. We're trying to get over to milliliters of sodium phosphate. And of course we still have the molarity left to go. The molarity here is 0.175 molar. Where's that 0.175 going to go? On the bottom. Because what it means is that there's 0.175 moles of the sodium phosphate for every 1 liter of the sodium phosphate solution. Well, of course, we want to wind up with milliliters, so the easiest thing to do here is to remember that 1 liter is the same as 1,000 milliliters. And upon doing so, the moles of the sodium phosphate wind up canceling out. And what else do we see that would cancel? It's a big fat number. 1,000 would cancel, right? We got 1,000 here. Cancel with 1,000 right here. Now the units don't cancel. These units still remain intact. They're the only ones left there. But now we should be able to multiply this through. We would take the 95.4 and go ahead and run this through your calculators. Anybody needs to borrow a calculator, I have some up here. I do need some collateral though, if you do borrow from me. It seems like between the first test and the second test, a few of you forget how to multiply in dimensional analysis. So we'll take 95.4, we'll multiply it by 0.102. We'll multiply it by 2 and divide it by 3. And looks like we'll divide it again by 0.175. And if I've done this correctly, looks like I'm winding up with 37.0697, blah, blah, blah. How many sig figs should we have? 3. So I'd round this off to be 37.1 milliliters of the sodium phosphate solution. Any questions on this one? Any questions? All right. Then the next problem in your packet here, this is one that I'm going to just say do this on your own. Again, this is on your own. For this particular one, just remember that this is going to be a limiting reactant problem. As a limiting reactant problem, that means that the amounts of both reactants are given. So we have the amount of the the potassium chloride given, and we must have the amount of the lead nitrate solution given. So kind of in a nutshell, how you might go about doing this is to go ahead and figure out which one. What are we trying to find in this one anyhow? The theoretical yield of lead chloride. So means if we're going to calculate the theoretical yield of lead chloride, this is a solid. That means we're probably going to be calculating this in which units? Grams, because solids would be measured on a balance. So we'd be measuring this in grams. So basically you're going to take these amounts here of each of these reactants. You're going to calculate two answers. One to see how much lead chloride can be produced from this amount of potassium chloride, and then how much lead chloride can be produced from this amount of lead nitrate. Once you get the two answers, what do you do with them? Pick the smallest one, right. You pick the smallest one then is your theoretical yield. All right, so any questions on the concept of this one here? And if we have enough time for this one, we'll come back to it as a review for your exam on, what is it, a week from Thursday?
Yep.
All right, next up, we're going to be looking at dilutions. And your text has a couple formulas on dilutions. One of the formulas looks like this: m sub 1 times v sub 1 equals m sub 2 times v sub 2. I like to write it a little bit more general. I like to write c sub 1 times v sub 1 equals c sub 2 times v sub 2. And when I write it like this, part of the reasoning for writing it like this second way is because, once again, this is a more generalized formula than the first one. But in all cases, M stands for molarity. V would stand for volume. The volume here can be in any units as long as the units on the two sides are the same. If we use C instead of M, C stands for concentration. And the concentration can be almost any units. It has to be a volume-based concentration, one that's based on the concentration of the solution. But as long as the units on C1 and C2 are the same, we can use this instead. And likewise, any of the units will work for volume as long as the volume units on the two sides are the same. So real quick question before we begin, because it's real important as you evaluate your answers. You want to always ask if your answers make sense. So if you dilute a solution, final concentration of the solution is blank compared to the concentration of the initial solution. So think about this. If you need to ask a neighbor, that's all right. You dilute something down. The final concentration is what compared to the concentration of the initial solution? Get your answers locked in. We'll count down. 5, 4, 3, 2, 1. All right, good. So that means you should remember when you check your answers and you dilute something, the final concentration is always less than its initial. Secondly, if you dilute something, the volume of the diluted solution is always blank compared to the volume of the initial solution. You see, with 97% of you getting it right, that means come exam time, I shouldn't expect to find 50% of you getting it right. So we'll count down here. 5, 4, 3, 2, 1. Well, it's going to be greater. If you dilute something, you're adding water. If you add water, what happens to the volume? It increases. You're going to get a bigger volume. So I don't know how we get 97% of you getting the first one right, only 72% the second one, because if one goes up, the other has to go down. Because, of course, as we look at this, this is inverse proportion right here. This represents an equation of an inverse proportion. As one goes up, the other goes down. And by the way, a subscript of 1 stands for initial or before dilution. A subscript of 2 stands for final or after dilution. Okay, so let's go ahead and do these. I'd like to know, what is the concentration of a solution prepared by diluting 25.0 milliliters of a 200 part per million mercury 2 solution to a volume of 2.00 liters. So we start with our dilution formula. C1 times V1 is equal to C2 times V2. And before we get too far here, we should ask, what are we looking for in this problem? Concentration. And are we looking for the initial or the final? We're looking for the final, so we're looking for C2. So that must mean that this concentration here would be C1. And the 25 milliliters must be V1, and the 2.00 liters must be V2. So before beginning any of these with this formula, I always recommend that you go through and label each one so you know what it is you're looking for and what you're given. So at this point we can rearrange this equation, solve for C2. To get C2 by itself, we divide each side by V2. V2 cancels, so it tells us that C2 will be equal to C1 times V1 all over V2. So we plug in the numbers. C1 is 200 parts per million of the mercury 2 solution. V1 is 25.0 milliliters. And we divide that by 2.00 liters. Of course, now what do we need to do before we calculate anything here? Convert. And what are we going to convert? Liters to milliliters or milliliters to liters. It doesn't matter. Just remember that your volumes must be the same units. For me, it's always easy. I hate dealing with fractions. If I can avoid numbers less than 1, I do. So I'm going to take the 2 liters here. I have 2.00 liters and convert this to milliliters. So how many milliliters are there per liter?
1,000.
1,000. So we have 1,000 milliliters for every 1 liter. And at this point, the liters cancel out, and we have 2,000 milliliters. So this 2.00 liters is the same as, the 2.00 liters is the same as 2,000 milliliters. So now that we have the same units, numerator and denominator, units here will cancel out. We then go ahead and calculate this by taking 200, multiplying that by 25, taking the result and dividing it by 2,000. We wind up with an answer 2.5. How many sig figs should the answer have? Looks like 3, because this number has 3. With a decimal, this has 3, this has 3. So our answer with 3 significant figures would be 2.50. The label would be parts per million of the mercury 2 ion. Okay, any questions on this one here? Okay, let's try the next one. Go ahead and give this a shot here, and see how you do here on the second part of this question. I'll give you about 2 or 3 minutes. This should be a relatively easy problem. Anybody not get the handout from last Thursday? Came in late, there was another handout for today. Anybody need the handout from today? little half sheet. Maybe about a minute and a half. Once you start cranking out answers, compare with neighbors. Make sure you're on the same track. All right, let's go ahead and check our answers. Answers to the first part. What volume? 150 milliliters, exactly. How many sig figs should it have? 3. So to show 3 sig figs, we could either put a decimal at the end or what else? Scientific notation, which we write it as 1.50 times 10 to the second milliliters. So that's for part 1. Part 2, assuming the volumes are additive, what volume of water is needed to prepare this solution? How much is it? 2.85 liters. All right. If we put it in units of milliliters, it would be 2.85 times 10 to the third milliliters. Okay, any questions on either of these? Going once?
Where do you get the second answer?
How do we get the second answer? Okay, well, if we got the first answer as being 150 milliliters, and we assume that the volumes are additive, we'd like to know what volume of water is needed. What volume are we trying to prepare altogether? 3 liters. So we know that the total amount is 3.00 liters. This is the total. We know the amount that is the solution, which is 150 milliliters of the, which one is this? The 2.00 molar sodium carbonate. So how do we get the 2850 or the 2.85? We subtract, exactly. Of course, because these aren't in the same units, we need to make sure that they're in the same units. So we could change this one here to 0.150 liters. And then if we subtract, we wind up with a 2.85 liters of water as your answer. Okay, anybody else? Okay, going once. Twice. All right, we are going to move on to a different topic here now. And do remember that you should be practicing this one here on your own. I like this one because it combines a number of different ideas together, like limiting reactant molarity, molar ratios. In fact, in this one you have to use the concept of limiting reactant, molar ratios, molar masses, all of them in there to arrive at your result. Okay, and I like, when possible, to combine ideas on exams. Okay, first thing we're going to do here, we've not seen this, I don't think, in this class. This is usually a intro course thing that I do day one. But I'm going to put the explosion screen up here. And the explosion screen is not so much for explosions today, but it's more for splash protection. And I need to have some goggles on myself. And what I'm going to do is I'm going to take a beaker here, and into this beaker I'm going to put some water. And this, of course, is the purified water. And we want to test to see whether or not this conducts electricity. So the question I have for you is, does pure water conduct electricity?
No.
Well, how do you know? The chances up here for you to put your answer in. So put it in, talk with a neighbor. Looks like we got 33 of you locked in here, so we'll check it out. Count down, 5, 4, 3, 2, 1. Looks like 84% of you are following Jacob's lead. All right, but 16% of you say yes. And so the device we're going to use is this light bulb here that I have plugged. This was very old when I arrived here, like 25 years ago. And so it's even older now. But I've had the same light bulb on here for 25 years. And these are some metal prongs hanging down, and if we complete the circuit on this, we see that the light bulb lights up. So what I'm going to do here now is I'm going to take this water, and since we've kind of reduced the drama now, we can still find out here whether or not this conducts electricity or not. See if 84% of you are right. And we see that water by itself does not conduct electricity. And why does it not conduct electricity? Any ideas? Because of course you've probably heard your entire life we should probably be keeping radios and stuff away from the side of the bathtub. Blow dryers. Yeah, Jacob.
Because it doesn't have any electrolytes in it.
Okay, and so that must mean that if we go over to the tap water here and try some tap water would in fact contain some electrolytes, and we see the light bulb go on. So what we're going to do now is we're going to go back here to the tap water, the pure water, and we're going to check to see a few different substances whether or not they conduct electricity. And we're going to try to not say it out loud this time. Okay? But we're going to have you predict which of these substances, either the sucrose, which of course is sugar, or table salt, is an electrolyte. And of course we haven't even defined it yet, because here it says will cause the water to conduct electricity. And that's because, talk with a neighbor. And here at the bottom, I'm going to write down the definition of the word electrolyte. An electrolyte is a substance that conducts electricity. When dissolved in water. So an electrolyte is a substance that conducts electricity when dissolved in water. And we'll come back here to your choices. We still have about 10 of you that need to get your answers locked in. So make your guesses. Which substance, when dissolved in water, will cause the water to conduct electricity? We'll count down. 5, 4, 3, 2, 1. And it looks like we're kind of all over the place here. Okay, so the best way to find out, of course, is to test them. So that's what we're going to do. And we'll see what we wind up with. So I'm going to go ahead and put water into each one of these. And I'm going to use, of course, the deionized water in this one because I don't want to start with either one of them that conducts electricity at the beginning. So we'll just test these very quickly to make sure that neither one conducts. And then we'll go ahead and pour some salt. This is on your left. Which one's first? Sugar. All right. We want to make them so they're in the same order. All right. So you have the salt here on your right, and I'm going to put the sugar here on your left. And we'll dig into this one here. Looks like we got enough there. And I don't have enough room in this glass. So we'll put this to the side. And we'll go ahead and mix these up. So clean this off. Mix in, dissolve the sugar. And then we'll clean this off. And we'll go ahead and mix up the salt. Now what we're going to do is we're going to make a table here. And in the table, we're going to list the substances, and we're going to tell whether or not they are an electrolyte. So we'll label them as an electrolyte or non-electrolyte. And we'll start here with the C12H22O11, which again is the formula of sucrose. And then the next one is NaCl, which is salt. So we'll try each one of these here, and we'll start with the sucrose. Oh, we need a drum roll here, please. There we go, thank you. And we see that this one here is a non-electrolyte. So those of you that correctly guessed on that, you can write that down. This is a non-electrolyte. And go ahead and check the sodium chloride. Drum roll again, please. There we go. Oh, that was pretty lame. Better one, yeah. There you go. And we see that this one here is an electrolyte. So now, we have a couple substances we've tested. We have a whole bunch more here that we're going to test. And so, what I'd like for you to do on the next list, so the correct choice here would have been? NaCl would have been choice B. All right, next up. These are the next 1, 2, 3, 4, 5, 6, 7, 8 that we're going to test. See if you notice any patterns, and I think you can select more than one on this one. So talk with a neighbor and select all the ones that you think would be electrolytes. And you can add them to your table. So again, add these all to your table. We're going to go through them in order. All right, let's get your answers locked in here. We got about 15 of you left to go. You can select as many as you wish on here. All right, we're going to count down on these. Get yourself committed. 5, 4, 3, 2, 1. It looks like we're kind of all over the place on here. So let's go ahead and test these, because hopefully now, as you go down the list, you're going to start recognizing a pattern. And we're going to start with the potassium nitrate. So potassium nitrate, KNO3. We'll put some water in here. We'll check to first of all make sure that the water by itself doesn't conduct. And then I need to clean off my spatula. I will go ahead and add in some potassium nitrate. Take a couple scoops here. And we'll go ahead and mix this up. Yeah, I'll grab right onto them. All right. Okay, and we'll, yeah, see, I've heard that one before. Okay, we'll go ahead and check this out. Ready? This one here is a strong electrolyte. Strong electrolyte. Next one, we're going to grab the copper 2 sulfate. Copper 2 sulfate. So this one here, I need another beaker. I don't have one. So we'll check this real quick to make sure that the pure water itself, see, cleaning it off. And we'll add the copper 2 sulfate to this. And let's see, by the way, we need to put in our correct result. What do we find for potassium nitrate?
Electrolyte.
Electrolyte, good. So let's try the copper 2 sulfate. And we see that this one also is an electrolyte. Anybody know what C2H5OH is? Ethanol, good, ethanol. All right. So let's check out the ethanol.
Don't drink it.
Don't drink it. Yeah, you never want to drink the ethanol we have in lab, because in lab we have denatured ethanol. Denatured ethanol means that we made it unfit for human consumption. And why would we make it unfit for human consumption?
We don't want drunk people in the lab.
Exactly. We don't want people drinking in the lab. Now, it used to be that they would denature it with some methanol. Problem is with methanol is methanol would make you go blind. Okay, so instead we denature it with something that makes you have severe diarrhea. Okay, so, right, so unless you like it, stay away from this. You're going to get very ill. And we check, oh, so now you go out drinking on a Friday night. Of course, most of you are too young, so you don't. But if you did, you were old enough and legal and had too much to drink, would ethanol supply you some electrolytes? How many think it would? Well, some of you thought it would, right? Some of you thought that, yeah, at least 4% of you did. And we see that it is a non-electrolyte, so don't go out drinking and think you're going to replenish your electrolytes. Now, by the way, why in the world would we need electrolytes? Because after all, the definition says that an electrolyte is a substance that conducts electricity when dissolved in water. Why do we need electrolytes? Something that conducts electricity, yeah.
Or like nerves, so electrical senses throughout our body.
Yeah, right. And not just our nerves, what else? Brain, our muscles. If we want to figure out what's going on with our heart, we take an EKG, right? We look at the electrical signals. So your body is one big mess of electrical signal. Not a mess, a big organized thing of electrical signals going on.
It's an organized mess.
So, yeah. but ethanol is not going to replenish your electrolytes. So if we go back then and think of where have you heard of electrolytes before? Gatorade. So now you think about who drinks Gatorade, or how do they market it? As a sports drink for athletes. Well, what is it that athletes do that warrants the need for electrolytes?
Sweat a lot.
They sweat a lot. And if you taste your sweat, how does it taste? Salty, right. So when you lose the sweat, you are losing some of those things that conduct electricity in your body, make your muscles work and everything else, your heart, your nerves. So you need to replenish those electrolytes. And you might say then, well, I've tasted Gatorade before. It doesn't taste very salty to me. It tastes pretty darn sweet. But of course, you ever tried drinking salt water before?
Yes.
Yeah. And how does it taste?
Salt.
Not very good for most people. So if you want to make it more palatable, what do? You add sugar. All right, you add a little sweetener to it to make it more palatable. And of course, the sugar just doesn't go to waste either, because if you're an athlete, what else do you need?
Carbs.
You need carbs. You need energy. Exactly. So you need energy. Your carbs then are supplied by the sugar in there, and the electrolytes supplied by the salt. Yes.
When I was a little kid, I went to the hospital because I was dehydrated once, and they made me drink a bunch of Gatorade. Why?
Well, probably if you were really sick, did you say, or dehydrated?
Yeah, dehydrated
Yeah.
from being sick.
Lots of times when you're dehydrated, I mean, what precedes being dehydrated?
Not having a lot of water.
Right. Probably, or a lot of vomiting in many cases, right? And if you vomit, lots of times you think of, if you ever tasted your own vomit, it's very concentrated with all sorts of electrolytes and everything that come up out of your body, and so it's just a way then to replenish those electrolytes. Okay? Not that we run around tasting vomit, right? Okay.
Well, I mean, you kind of have to.
All right. So now, any connection we're drawing between electrolytes and non-electrolytes? Metals. All right. So in other words, if we look at these, it's a little bit more than just metals. Ionic compounds. Right. Our ionic compounds are the ones that are tending to be electrolytes. So this brings us to the next one here, which is calcium carbonate. And even though I don't have a chalkboard in here anymore, I still carry around my chalk that's like about 20 years old. And what I'm going to do here is I'm going to take this piece of chalk and I'm going to put this chalk into some deionized water. We'll check very quick, first of all, to make sure that this is not conducting. It's not. So we'll pop in the chalk. And now the chalk is not super soluble. So what I'm trying to do here is I'm trying to break the chalk up into some smaller pieces and just get some of the chalk here to dissolve. And we then want to test to see whether or not this conducts electricity. And when I do this, in fact, I'm going to turn the lights down so you can, well, that's enough there. We'll test this. And we see that the chalk itself does not conduct electricity. Now, this is where sometimes students go a little bit astray with this, because we've just established that ionic compounds are electrolytes, but there's a little caveat to that.
They have to be dissolved in water.
They have to be dissolved in water. If you go back to your definition, the definition says an electrolyte is a substance that conducts electricity when? Dissolved in water. And if it doesn't dissolve in water, it can't be an electrolyte. Yes?
Does calcium carbonate dissolve in anything else?
It could.
Would that substance be conductive then?
Well, if we took some calcium carbonate and I don't know if we can create molten, I don't think we can create molten calcium carbonate, but if we could, molten calcium carbonate would conduct, because what we need is some mobile ions in order for it to conduct. I think that calcium carbonate would probably decompose before we actually were able to melt it. Okay, so calcium carbonate, this one here we say is a non-electrolyte, but put down your qualifier on this one. It's a non-electrolyte because this here is insoluble. And again, in order for it to conduct electricity, it must be dissolved in water. Okay, then that takes us to HC2H3O2. What is the name of this substance? HC2H3O2. Acetic acid, right. So now what I'm going to do is I'm going to take some water and test the water, and then I'm going to take the acetic acid. This now is pure acetic acid, and I'm going to walk around here to see if you can identify where we find acetic acid. Where do we find acetic acid? What does this smell of? Vinegar, right. Acetic acid is the acid found in vinegar. Okay, this is the acid found in vinegar. So now, the difference though is that this acetic acid is 100% acetic acid. If you look at a bottle of vinegar, right here, the bottle of vinegar will say it contains, it's reduced to or diluted with water to 5% acidity. So this here is only 5% acetic acid. This here is 100% acetic acid. So what I'm going to do now is I'm going to take the acetic acid, put it in here, and we'll stopper this up. Again, we'll test the pure water right here. We'll test.
Acids were only called acids when they were dissolved in water.
That's only the case for binary acids. Oxyacids have their acid name all the time. Okay, so we see here that neither one of these conduct electricity. But now if I pour the acetic acid into the water, we see that it winds up conducting. Okay, now compare though the brightness to what we saw. This one is weakly conducting, whereas if we go back to the salt, whoops, that must have been the sugar. Number 2 is the salt. There we go. This is the salt. This here now is the acetic acid. This one is weakly conducting. And at this point, we go ahead and make a distinction between those that strongly conduct and those that weakly conduct. And the acetic acid here is a weakly conducting solution. We say that this one here is a weak electrolyte. This is a weak electrolyte. And so that means you should go back and relabel all the ones we did previously as strong electrolytes. And this one here is a weak electrolyte. And the previous ones we did here were all strong electrolytes. So strong, strong, strong. And a strong electrolyte is one that strongly conducts electricity. That means there's a very strong current that passes through. Let's try NH3. Let's try NH3. Now NH3, oh shoot, did I get this one? I think I forgot to grab NH3. We can't do NH3. Oh, yep, here it is. NH3. What is NH3 commonly known as? Ammonia. So if we go ahead and take some ammonia, and we'll go ahead and put the pure water in. We see the pure water doesn't conduct. And I'm going to stand back here just a little bit on this one, because I don't like the smell of concentrated ammonia. If we check this one out, we see that this too is a weakly conducting solution. Now you see we have a little problem. We just gone back and said if it's an electrolyte, it must be ionic. And clearly now we have 2 molecular compounds in a row that aren't ionic. These are molecular compounds, which we found are weak electrolytes.
Acetic acid is ionic.
Acetic acid is not ionic. It is a molecular compound.
Or at least,
When we have non-metal to non-metal, This is a molecular compound. They are joined by covalent bonds, not by ionic bonds. Okay, next up, we'll look at HCl. HCl is also a molecular compound. And if we check out HCl, and again, I don't like to breathe this directly. So we look at the pure water not conducting. We'll pour this one in. And we see that this one here is a strong electrolyte. Yeah, that one you could even hear the sparks. Okay. And then the last one we're going to do is going to be sodium hydroxide. Sodium hydroxide. And of course, as we're labeling this here is a strong electrolyte. And if we do this last one now, we'll place some water into here. We'll test this quickly to see that the pure water by itself does not conduct. We'll add a small amount of NaOH to this, and we'll mix it up to get some of the sodium hydroxide to dissolve. Now this one, there's no tricks or anything else. This one behaves according to what we know traditionally. Should this one be an electrolyte? Yes, it should, because if it's dissolving in a ionic compound, we should see, in fact, that it is a strong electrolyte.
How hot's the water?
This one does get a little warmer. It depends upon how concentrated we make the solution. So the thing here to point out on these three is that these are molecular compounds. And these molecular compounds still were electrolytes. And it turns out that if we were to define electrolytes a little further down here, we say that in order for a substance to be an electrolyte, ions must be present in solution. So ions must be present in solution in order for it to be an electrolyte. So the big question then becomes, what does that mean or imply about these three molecular compounds? In other words, if these are molecular compounds, and we say that ions must be present in solution for it to be an electrolyte, what does that mean happens to these three right here?
They form ions.
That must mean that they form ions, and that means that they have to go through a reaction that forms those ions as a result. So here's where we're going to go with this. First of all, any questions on the demos? All right, here's where we go with this. First of all, we define an acid as being a substance that produces H3O positive when dissolved in water. And it looks like I need to squish this down a bit. This is where a tablet PC is really nice. And we say that a base is a substance that produces OH negative when dissolved in water. Now, of course, one of these we've looked at already. Which of these ions have we looked at already? H3O positive or OH negative? We've looked at this one. What do we call this one? What is this ion called? This is the hydroxide ion. In fact, I should probably put this in blue, because blues identify with bases. So this here is the hydroxide ion. And what is H3O positive? one's hydronium. Here's the hydronium ion. And now this one is new to us in here. The hydronium ion, this is a substance that is only present in aqueous solutions of acids. So the whole hydronium ion is an ion that is only present in aqueous solutions of acids. And what that means is that if we were to try to make a compound like hydronium nitrate or hydronium chloride or hydronium sulfate, we can't make it. Because as a compound, the hydronium ion would never exist. It's only an ion that's present in the solution. And so to describe what happens if we look at some of these molecular compounds, we could write out a couple of equations. Let's start first of all with the acetic acid. We're going to write out equations for these four substances right here at the end to show how these act as either an acid or as a base. And so we'll start with this first one here, which is acetic acid. So now, if we want to write out an equation for the acetic acid, what we're going to do is this. We have HC2H3O2, and we dissolve this in water. Because it's a molecular compound that conducts electricity, that means that it must react with water to produce ions. And because this is an acid, that means that one of the ions that is produced is which type? Hydronium. Right. And so we wind up producing hydronium ions, and if we balance this equation, what's going to be left over? C2H3O2 with a charge that is negative. And that's aqueous. And so we wind up with hydronium ions and acetate ions as the product. So this is what happens, once again, when we put acetic acid into water, and that accounts for its ability to conduct electricity like we saw. We do the same thing with NH3. NH3 now is a base. NH3 is a base. And if it's a base, we saw that, we go back to the NH3, which I think that was, kind of lost track of these. I think it was this one. Oh, I unplugged it anyhow. Never mind. But we saw there was a weakly conducting solution. That must mean it contains ions. If it's a base, what ions must be present? Hydroxide. So you know the hydroxide ions are present. And what's going to be left over in this case? Ammonium ions, right. And ammonium ions would be NH4 with a charge of 1+. Okay? So we end up producing ammonium ions and hydroxide ions. If we do the HCl is a molecular compound. When we react this one with water, HCl we classify as acid or base? Acid. It's an acid. So if it's an acid, that means it's going to produce hydronium ions. What's going to be left over?
Chloride.
All right, chloride will be left. And then if we look at the last one in our list here is the NaOH. The NaOH, though, is not a molecular compound. This one is an ionic compound. So to show what happens in an ionic compound, we'd simply say that the sodium hydroxide here that's present in water, we'd write H2O above the arrow. We show that that causes it to separate into sodium ions and hydroxide ions. There's no real reaction that takes place in this one, whereas in the first three here, chemical reactions did take place. And so we're going to introduce some terminology here. The terminology looks like this. We say that these three reactions, the first three, represent the process of ionization. First three represent the processes of ionize. You can spell this, ionization. There we go. These represent ionization. And the last one here represents what we call dissociation. And so to make a distinction between them, here's what we do. First of all, when we ionize something, that means we're making ions out of something that wasn't ionic to begin with. So if you ionize something, that means you're making ions out of something that wasn't ionic to begin with. So you see these reactants right here, these are not ionic. Okay, these are molecular compounds. But when they react, they wind up producing ions. So that's what we mean by ionization. They go through the process of ionization. Now, dissociation is different. If you dissociate yourself from something, what does it mean if you dissociate yourself? You separate them, right? So maybe you don't agree with someone, so you dissociate yourself, no longer have a relationship with them. Dissociation means to separate or go apart. So sodium hydroxide is already an ionic compound. When you place it in the water, that ionic compound simply separates into its ions. So that's the difference here. Again, the first three represent ionization because these show molecular compounds reacting to form ions. The last one here shows an ionic compound simply separating into ions. Now, in each case, what makes an acid or a base is, if it's an acid, it contains hydronium ions. If it's a base, it contains hydroxide ions. Now, a couple other things. First of all, of these four reactions, or these four substances we looked at, which two are the weak electrolytes? Which two are the weak electrolytes? Go back to your data. Which two are the weak ones? All right, the acetic acid and the ammonia. So for each one of these here, we actually put in a double arrow, like this. Okay, so for the first two, we actually write in a double arrow. Now, we don't talk a lot about what this double arrow means in the first semester. This is more of a second semester course. You'll be talking about equilibrium and equilibrium reactions, equilibrium constants and stuff in the second semester of this course. In the first semester, the way we can think of this is that this represents a reversible process. And it's important for us to recognize this as a reversible process, each one of these, because if these are weak electrolytes, that is, both of these two are weak electrolytes, what does that tell us, relatively speaking, about the amount of ions in solution? A whole bunch or very little?
A little.
A little. Because if we had a whole bunch, what should happen to the light bulb?
Brighter.
Should be very bright. Because again, the brightness of the light is an indication of the amount of ions in solution. If there's not many ions in solution, then that bulb is not going to be very bright. Yes?
So is the concentration of ions in a given solution what determines its ability to conduct electricity?
Exactly. And not all substances have the same ability to conduct electricity because they dissociate or ionize more to a greater degree. So what we'd say in the case of HCl, HCl is one that ionizes completely. So HCl and H2O, this is a very complete reaction. The bonds that form here between the atoms here to form ions actually, this is a stronger arrangement than the bonds that are present in these substances. Whereas in these here, actually there's only about 5% ionization that occurs, or maybe even less. Maybe it's only 1 or 2%. It's one of those things you calculate, but I think that's a second semester concept that you do. So we find out that only a small proportion of these actually ionize, and that most of what is in these, if I were to pick up the ammonia now, if I were to pick up the ammonia and smell it, which I think it's this one here, I can still smell the ammonia in here. And the reason why I can still smell ammonia in this one is because most of it are still the molecules. Whereas the HCl, this was a super strong smelling stuff. This was the stuff that I had to hold at an arm's length. If I smell the molecular stuff here, I mean, I'm going to be overcome by the fumes. But if I picked up that solution that has the HCl in it now, I can smell it, and I'm not going to get overcome by the fumes because this reaction here pretty much went to completion, and these ions stay in the solution. So there's a number of different ways we can wind up detecting that. When you smell things, typically what you're smelling is molecular substances, not ionic substances. Okay. Any other questions? Very good. Any others? Okay. Here's a couple more things before we go today. If we want to know what this hydronium ion is all about, let's go ahead and draw the picture of a hydrogen atom. Let's draw the picture of a hydrogen atom. If we look at a hydrogen atom, now remember there's multiple isotopes of hydrogen. The most abundant isotope of hydrogen is hydrogen 1. That's hydrogen 1. So if we go back and drew a structure of a hydrogen atom, what are we going to find in the nucleus of a hydrogen atom?
Proton.
1 proton, right? And out in the electron cloud, how many electrons are we going to find? 1 electron. And of course that's because the atomic number of hydrogen is 1. So now, let's go back and find out what happens here. What I'm going to do is I'm going to erase this electron. When I erase this electron, I wind up forming a hydrogen ion. Because, again, an ion is an atom that has either gained or lost 1 more electron. Well, in the case of hydrogen, we can see that a hydrogen ion is also the same as what? It's the same as a proton. So a hydrogen ion and a proton are the same thing. Okay, now the problem is, and I think we went through this analogy when we were talking about the sizes of atoms. I think we talked about, if we compared the size of a stadium, like the Metrodome or US Bank or Target Field, as being the size of an atom, then the nucleus would take up the space of a housefly. Okay, so we're talking about a huge dramatic difference between the size of an atom and the nucleus. So what happens now, once we get rid of this electron cloud, we're just left with a bare naked proton. And that bare naked proton is super, super concentrated in charge. Okay? Well, because it's super, super concentrated in charge, and the charge in this case is positive, this positive charge is going to seek out something that is negatively charged. And in the case of water, what happens is that if we put an acid in water, it turns out that water has a shape like this, and we'll be talking more about electron geometries and electron dot structures later on in this course. But these dots here represent pairs of electrons that are on the outside of this oxygen. Well, it turns out that this proton really, really likes those electrons out here on this water molecule. And as a result then, what happens is that that proton winds up attaching to that water molecule, and the end result, once that proton attaches, is the hydronium ion. So the hydronium ion is the result of this proton attaching to electrons of a molecule of water, yielding the hydronium ion. So this is what the hydronium ion has for a structure. Again, compare that to the structure of H2O, which looks something like this. Now the last thing we're going to look at here today is this, and that is some terminology, and that is the term strong acid and weak acid. Strong acid and weak acid. And we can kind of make a table here. Strong acid, weak acid, strong base, and weak base. Now, here's where the definitions come from. We say that a strong acid is an acid that is a strong electrolyte. A weak acid is an acid that is a weak electrolyte, which means that a strong base is a base that is a strong electrolyte, and a weak base is a base that is a weak electrolyte. So when we use the terms strong and weak as they apply to acids and bases, we're talking about how they are as an electrolyte. So based on that, of the four substances we looked at here at the end, let's go ahead and classify them into their proper categories. Which one of these is a strong acid? Which one of these right here is a strong acid?
HCl.
HCl. Which one is a weak acid? Go back to the list. Which of these here is a weak acid? Well, let's go back to our list of reactions.
Acetic acid.
It's going to be the acetic acid because, of course, acetic acid produces hydronium ions. So the acetic acid is going to show up here. Which one's going to be a strong base?
Used to be.
Which one of these here? Let's see. We have two bases. We have the NH3 and the NaOH. Which one is the NaOH? Because the NaOH was the strong electrolyte. And that means that the NH3 must have been the weak base. Okay, again, it has to do with the strengths of the electrolytes. Now, what you're going to do is you're going to memorize your strong acids, your weak acids, your strong bases, and weak bases. But we're going to make it hopefully relatively easy for you. The strong acids you should memorize are these right here: HCl, HBr, HI, HNO3, H2SO4, and HClO4. So these are your strong acids that you should memorize. Now, if you memorize these 6, pretty much all other acids fall into this category. So any other acid that now that's not entirely true, but at least in this course here, unless you're told otherwise, any other acid that you encounter is going to be a weak acid. Now, of course, one of those we saw was acetic acid, but onto this list you could also add H3PO4, HF. I like to put down HF because if you've thought that all of the hydrohalic acids were strong acids, they're not. HF is a weak one. And then for the strong bases, this here is going to be your group 1A and group 2A hydroxides. And what do we mean by group 1A and group 2A? That's where we look on the periodic table, right? So we look at the periodic table, and basically if it's a hydroxide in group 1A or 2A, then it's going to be a strong acid. Now there are a couple exceptions. The beryllium and magnesium hydroxide are exceptions. So we'd say except for beryllium hydroxide and magnesium hydroxide. And I don't know why that's disappearing. Let's bring it back here. So, except for beryllium hydroxide and magnesium hydroxide. And then over here, we'd basically say that all other hydroxides fit over here. NH3 is listed, and it turns out that there's many others that come under this category as well. So if I were to memorize anything, I'd memorize these two right here. Memorize your strong acids and your strong bases. So any other acid that you encounter is going to be a weak acid. Any other base that you encounter is going to be a weak base. And we'll start with these facts on Thursday, and we're going to apply them to chemical reactions.